So real quick, when we get to where the camera stops in the middle of the lecture, can you let me know? Because I've noticed attendance has been dropping a little bit since we started doing this. So what I want to do, this is on camera right now. So at the break, I'm going to show a question, not the answer. I'm just going to write a question and I'm going to put in the exam. And if you do not go to the lecture, you do not get that, guidance. And so I'm not going to do it every day, but I will do it sporadically as a half-witted attempt to try to get attendance up again. So let me know when the break's coming, and then we'll pause it, and then I'll show you a question that I'll be putting in the exam. Not the answer, but just something for you guys to think about and play around with.
You can stop whenever you want.
Yeah, but I feel it's natural just to do it in the middle. So those who are just watching online, I'm glad you're watching these, but if you get confused by something I say, you can't ask me a question if you're watching me on YouTube. So, coming to lecture is a good thing. So just give me like a little thumbs up when it's getting close to the break, and I'll temporarily stop. Sound like a deal? You guys are awesome in coming to class on a beautiful day like today, so I'm not opposed to Easter eggs every so often. No, I'm bound to it because of the camera though, right? Alright, so we stopped yesterday when we were talking about the chemistry of esters. And just a quick review of the traditional nucleophilic acyl substitution of esters. The group on the ester, the OR group, so O alcohol, O whatever, is going to have a pKa roughly 16 plus or minus depending on what our R group is. So in this case it's methyl, so the leading group would be methanol. Methanol has a pKa of roughly 16. So pKa of 16 for a leaving group, and we know the equilibrium of all of these reactions is determined by the difference in pKa's between the nucleophile, so the thing that adds in and becomes part of the acyl group, and the leaving group. So the thing that's originally on that eventually falls off. And so in this case, with the ester, since the leaving group when we start with an ester has a pKa of 16, we can take in the mean and go primarily to the amide, because the pKa of an amine going from neutral amine to amine minus is 36. And the pKa of an alcohol is 16. And so the equilibrium is going to be biased towards the side where the stronger base, i.e. higher pKa of the conjugate acid, is part of the acyl group. And so since the amine is part of the acyl group, in this case, the equilibrium is going to lie in favor of the ester being attacked by the amine, and then eventually giving us the amide. So with esters, we can take in the amine and form the amide fairly easily, and this will be a thermodynamically favored reaction as given by the difference in the pKa's between alcohol and amine. Conversely, with our ester, we can't, in theory we can take Cl minus or S8 minus and have it add in, but in those cases the equilibrium is going to be really disfavored. And the reason the equilibrium is going to be really disfavored, again, is the pKa reasons. Equilibrium is going to lie on the side with the stronger base being part of the carbonyl now, having a bond with carbonyl. Again, pKa of this is going to be 16, methanol. And then Cl minus, pKa of sub-zero, acetate pKa of 4. This equilibrium is not going to be able to favor these because the weaker base, if we're going from here to here or here to here, now the weaker base in these cases is forming a bond to the acyl group, whereas the stronger base is not, is now swimming around. And since the stronger base is now swimming around, if we form these, the methanol or the MEl minus which fell off is just going to go and attack these respectively to give us the product anyway. So the equilibrium, when we try to add a weaker base to a carbonyl with a stronger base as the leaving group, it's not going to do anything. It's just going to stay in the ester, and the Cl minus and the sodium acetate are not going to add in, and the equilibrium is just going to favor the starting material. So this is a review. pKa's are important. The stronger base is going to form the bond. the weaker base is not going to form the bond in the product. So that led me to asking a question at the very end of lecture. It's really a review of stuff you did in the lab. The question is, what would the equilibrium look like if you took an ester and soaked it in water? Would we expect this to be a favorable or a disfavorable reaction, or just kind of black, kind of neutral? Kind of neutral, because pKa reasons, if you just look at the pKa of the group that's bound to the acyl group in each one, we have methanol, 16, and water, 15.7. So this is OH. Add a proton, replace this with the proton, H2O, 16. This is NEO, replace the acyl group with the water, this is methanol, pKa of 16. So the basicity of the leaving groups in each of these is very similar, 15.7 versus 16, so very, very subtle difference. And so basically, if we do this, you'll just get eventually some kind of mixture of methanol and ester and carboxylic acid, with nothing really driving the reaction forward. They're just going to have one-to-one mixture, something along those lines based on pKa's. Kinetically, assuming you can overcome the energy barrier, to actually go from here to here. If you have enough energy, it will go back and forth, back and forth, back and forth, and the reaction won't be able to make up its mind. So, conversely, so let me actually do these in different colors, the equilibrium in different colors. And of course, this equilibrium also is true if you take a carboxylic acid and dissolve it in methanol. You'll have some kind of, assuming you get over the energy barrier for a reaction to occur, you'll just have some mixture, pKa-wise. So, is there a way to get over this? How would you find a way to bias this reaction either way? Yeah, well, first off, Le Chatelier's theorem, but you still need to overcome the energy barrier.
So heat?
You still need to be able to react. So you can heat it. You can definitely heat it. Or, in general, you can combine heat and acid catalysis. I believe that's what we did in Chem 432 lab the first week with the Fischer esterification. And so the Fischer esterification is pretty much this reaction right here, except you add some H+. Fischer esterification. So in the Fischer esterification, and let's go from this direction to the ester, because that's the traditional way we think of it, is going from a carboxylic acid to an ester. But I just want to point out, this reaction is completely controlled by Le Chatelier's theorem. So if you take a carboxylic acid and methanol with acid, you'll get the methyl ester. Conversely, if you take a carboxylic acid, if you take an ester in water with acid, you'll get the acid. So this reaction is completely controlled by Le Chatelier's theorem. It just depends what your solving conditions are. So just to show you the general mechanism, and let's start with the carboxylic ester. The carboxylic acid. With H+ and methanol. And just before I start this reaction, I just want to mention, I really hope this reminds you a lot of acetal chemistry. Because this mechanism is very much similar to an acetal mechanism, except it's a carboxylic acid rather than a ketone or a aldehyde. So just as with the acetal mechanism, the first step will be protonation by the H plus catalyst of the carboxylic acid with the H plus. Let me try this a little bit lower. So now, once we protonate the, yes?
How come the oxygen with the H is not more basic and labeled?
Oh, why is this oxygen not the one? Why does this oxygen take the proton and not this one? Well, really the answer is resonance, right? Both of these oxygens are sp2, right? Both of these oxygens are sp2 because this one is adjacent to the double bond and there's resonance. And so really, we can think of this carboxylic acid looking like this.
That one's partially positive.
Yeah, and so because this has a hydrogen, this is going to have a little more partial positive charge than this one will. Okay? So the carbonyl will take the hydrogen. And now, since this is now protonated, we are lowering the LUMO of this pi star orbital. So remember earlier in the class when we were talking about reactivity trends between carbonyls, and we said esters and amides were less reactive than ketones and aldehydes because of electron donation in the pi star orbital. And so it's harder for a nucleotide to add into an amide or an ester than it is to add into a ketone or an aldehyde. We talked about this early on in the class. So that's one of the problems with esters is they are fairly high in energy for a nucleophile to attack. And as I said earlier, in order to do all this chemistry, we actually have to have enough energy to be able to overcome the reaction barrier for the reaction to occur. But we need that for every reaction. We need enough energy in the system to overcome the reaction barrier for a reaction to occur. So in this case, though, since we protonated this oxygen and we have this H plus, we just significantly, we're incorporating a positive charge into the carbonyl system. That's going to significantly lower the energy level of this pi star orbital through a destabilization. You can imagine this positive charge in this oxygen is going to be spread out through this entire system, including the carbonyl carbon. So what we're doing is we're taking the carbonyl carbon that's already got a little bit of partial positive charge. In this case, and I'll draw this with a a typically sized partial positive charge of this carbon. And now that we've protonated this, I put a positive charge in the oxygen. By electronegativity, we know this positive charge being introduced through protonation is really going to lie on the carbonyl carbon. And so by protonating it, we just really increase the amount of the coulombic amount of partial positive charge on this carbon. And that's analogous, so that's just a different way of saying we just significantly lowered the energy level of the anti-bonding pi star orbital. And so since we've done that, now it will take less energy for methanol to go and attack that carbonyl. So you need to protonate first, and then the methanol can add into the ester, just like in an acetyl mechanism. All right. And so now that gives us something that really reminds us of an acetal, right? Or a ketal. It just has 3 oxygens instead of 2 oxygens. So you can imagine the mechanism for this next step doesn't change at all. It's just another proton transfer in equilibrium. And of course, these 2 OHs are equivalent, so it doesn't matter which one takes it. like so. And of course, this proton transfer is in equilibrium, right? And do you think it would be a good equilibrium or a bad equilibrium or a kind of blind equilibrium? Based on the pKa of this acid versus the pKa of this acid. That's pretty blasé, because hydronium here, very similar to hydronium, just methyl pushing off the hydrogen. So pKa-wise, it's going to be pretty neutral, so not too much is going to change. And so, this equilibrium will go forward to some degree. But once again, this is this Le Chatelier's thing. All right, let's stop right here.